Okay, we want to talk about Euler's method. And Euler's method is basically just follow the slopes. That's what we did originally. First thing we did in the course, basically. And you know how to do that. And I just ask you to do something and you're setting it up right. So you remember, here or there, you got good notes and you're copying them again. That's okay, you know, whichever. Just make sure you internalize this as best you can. Because we're going to develop a formula for this thing. The formula is not the primary thing. The primary thing is understanding that this is what you're doing. And if you know this is what you're doing, you can always write down the formula. And I prefer that you not memorize a formula and then blindly apply it, because you don't need to, because you understand this already. But there are things that we want to be aware of, because this is kind of our second pass on it when we're formally studying it. We want to be aware of the errors, and you looked at that. You know, we are aware that the smaller you make the interval, typically, unless you have some kind of pathological function, or there's some kind of a weird point, okay? The smaller your increment, the better your approximation, okay? So we want to be aware of that. We observed a bit of that. We compared our solutions with, you know, our approximate solutions with actual solutions to the equations, but we didn't analyze them, okay? So we're not going to analyze them too deeply right now, because it's only an introductory course, but we still want to be aware of them so you know how to analyze them, okay? Okay, so, and this is very important because the majority of equations that arise in real life have to be solved by some kind of numerical method, and Euler's method being the most basic method, not the most powerful, not the most efficient, but the one that's easiest to understand, and once you understand it, the others become fairly easy to understand, okay? You know, for example, Euler's method just projects along a straight line, okay? And then you have second order methods basically project along quadratic curves, okay? Not hard to understand. It's not hard to write down the algorithm. At some point, you lose track of just what the method is doing, how it's derived, what it means, but you know it's a higher order method, and then you have formulas that are similar to Euler's method formula, but more complicated, and sometimes you just got to kind of memorize that formula because you don't want to have to rederive it. For Euler's method, you know where it comes from, you know what it means, and so forth. So that's kind of what we're doing, okay? So anyhow, let's just take an example, very simple. Y prime equals t squared, simple equation that you can solve. It's separable. You're going to get t cubed over 3 plus a constant, right? And y of 0 equals 1, so that constant's going to be 1. So your solution's actually going to be t cubed over 3 plus 1. We're going to be able to compare that with Euler's method solution, which is going to diverge pretty well for h equal to 0.4, step of 0.4. So what I ask you to do here for a couple of minutes, I just drew a little picture. You are here, that's at 0, 1, and now you want to move on, okay, with a step of 0.4. That's a little hard to read down there at the bottom of the board. The board's a little rough. 0.4, 0.8, 1.2, 1.62, right? Here's a bigger picture. I didn't draw the bigger picture until I asked you to do it. And of course, first thing you did was you made tables, okay? You made a table of your y and your t and your y prime, and then you started doing what you know how to do. So that was very good. Glad you remembered to do that. Okay, so anyhow, here you are. I'm not going to make the table. I'm just going to do what the table tells you. Okay? If we evaluate y prime here, well, y prime equals 0, so the slope is 0 at this point. And that's at the point 0, 1, y prime is 0, the slope is 0, there it is, okay? So we're going to follow that slope. We follow that slope for 0.4 units. And no surprise, we end up with 0.41, right? So here we are at y prime is going to be, if 0.41, y prime is going to be 0.4 squared, that's 1.6. 0.16. I wrote it right and said it wrong. That's the reverse of what I usually do. So 0.16. Now let's see, what would a slope of 0.16 look like on this graph? Well, that would be like a run of 1, which is this much, and a rise of 0.16, which is maybe this much. Okay? So that's going to be a slope that looks something like this. It's pretty small slope. But because the one here is bigger than the one here, it's going to look a little bigger than it really is. Okay, hopefully you understand what I mean. So slope is 0.16. So we move over 4.4 units at a slope of 0.16, and we get to this point. The lines aren't very straight, but they're supposed to be, and we understand that. Okay? So, well, at a slope of 0.16, we move 0.4 units, so we must move 0.064 units in this direction. So, rise is this. There we are, right? And now, we're at this point. Now at this point is 0.8, 1.064. Okay? Now the slope is 0.8 squared, which is 0.64. So we have a slope of 0.64. Okay, I'm going to give up and try to make it look right. Okay, but here the slope is 0.64. And we follow that slope for 4/10 of a unit, which feels way off because my slopes are. Okay? Then we get a rise of 0.64 times 0.4, which is 0.216. Okay? 0.2. Sorry, 0.25. 0.4 times 0.64 is 0.256. 256, yeah, okay. Now I'm just going to say approximately 0.5. Actually, 0.25, 0.26. Okay? So now the point is 1.2, 0.26, and 0.064 is going to give me like 1.032, 1.32, not 032. And now y prime slope 1.44, etc. And the rise is going to be approximately 0.4 times that, so it would be 0.56, 0.576, 0.58. Okay. I think that's right. But okay, so that's going to give us a significantly greater slope. Okay, again, the picture's way off the scale, the y scale's way off. But we follow this out to the point where we're up above 1.6. That's going to give us 1.6, 1.9. So we're almost up to 2. So 2 would be here, 1's here. Again, the y scale isn't very good. And then we do one more step. 1.6 squared is 2.56. Okay? And 0.4 times that is very close to 1. Okay? So 1.16. And 0.4, 1 point. I'm losing track of my powers of 10. And I had a good night's sleep. But, so I have no excuse except, working memory. Okay, don't want to think that hard, it takes too long. Okay, at least not for class. Any place else, I'm thinking through, screwed up completely. Okay, so, 1 point, anyhow, we get a rise of approximately 1, okay? So we get a steeper slope here. And we follow this, and we go up here to the point 2. I'm going to say about 2.3, between 2.9 and 3. Okay? So we get a curve that looks like this, very plausibly a t cubed type curve, right? T cubed over 3. Okay? And since we know the real solution is t cubed over 3 plus 1, how does the approximation compare? Okay, well, here's t. Here's y approximation. And here's y exact, right? Okay, so well, at 0, y approx is 1, and that is y exact as well. At 0.4, our approximation is still 1, but the exact is 0.4 cubed over 3 plus 1. Okay? Well, 0.4 squared is 0.16, and 0.4 of that is 0.064. And then divide 0.064 by 3, and you get about 0.021, okay? So this would be about 1.021. We're not that far off, but obviously this thing doesn't stay, the actual solution doesn't stay flat all the way over here, because as soon as you move away from t equals 0, you're getting a positive slope. And we're just keeping the thing at this slope. Okay? Then at 0.8, our approximation, if I calculated it correctly, is 1.064. Well, 0.8 cubed, 0.8 squared is 0.64, square that, you get 0.512, okay? And take a third of that, you get about 0.17. So you're going to have like 1.17. So you see, you're really nowhere near, because what's happening is the slope is starting to increase a lot faster here, just like it does for the approximation, but even more quickly than that, because our approximations are all underestimates, and we've talked about that. Okay? So we're starting to get some separation between the exact and the approximation. And it's only going to continue to get worse, because as the slopes rise faster and faster, the underestimate gets more and more drastic. So without further ado, let's just write down some numbers. We've got 1.32 here, 1.9 here, and 3 here. Now, if we skip all the way down to the value of 2 and then ask ourselves, how did we get that far off? Okay? And it's not that terribly far off. Okay? 2 cubed is 8. You divide that by 3, you get 2.66 repeating, call it 2.7. Well, 2.6 repeating, right? And you add that to 1, you get 3.6 repeating. Okay? So, you're off. That's not, it depends what you're trying to do with this. You're trying to get a ballpark. Yeah, it's in the ballpark. Trying to build a bridge and you're over-designing everything by a factor of 3, that's acceptable. Although if you're doing the bridge, you're still going to use a computer to do this with a small a, right? And hopefully with a better algorithm. Okay? Okay. So, between here and here, your separation is going to increase. So, at 1.2 cubed is, it's 1.732. Yeah. Okay? Yeah. 1,732 cubic inches in a cubic foot. Okay? 12 cubed. Okay? And you divide that by 3, you get 0.5, 7, 577. Okay. So I'm going to get something like 1.58. I'll put a question on that. Okay. Now everybody knows 1.6 cubed because it's a power of 2 divided by whatever. Okay. 256 times 1.6 gives you about 4,000, right? That's 4,096, it's 4.096. Okay? So it's like 4.1. You divide that by 3, you get about 1.3, close to 1.4. That would give you like 3.4. That's high. What's going on here? Okay? That's like 2 to the 4th. 2 to the 12th is 4,096. Okay. Well, okay. I don't think our I'm going to fudge and say 3.3, although when I calculate, I get 3.4. I think there's something wrong with that calculation. I don't want to mess with it. We want to list the error of the approximation. our approximation is 0.021 log, right? Here, our approximation is about 0.11 log. Okay? I'm going to say approximately there. Here, it's about 0.16 log. And by the time you get down here, it's 0.6 log. And the thing disturbs me about this approximation should be 2 points. Okay, that would be like negative 0.4. So, I put a big question mark. Can't put a big one here, didn't do myself rude. A big question mark, a little one here. Not sure about this number and this number, because this grows from here to here, it grows from here to here, and then it grows too much from here to here and not enough from here to here. Okay, so something's wrong. It could be there's something wrong here, but kind of picked on it there. So you can, part of homework, fix my numbers up. Okay, just force you to review the process and see how the numbers develop. Okay? Now, the next question is, what happens to the way these errors grow if you go to a smaller increment? Okay? So we cut the increment in half to 0.2, we could do the whole thing again. And doing it by hand wouldn't be that tedious. Go down to 0.1, I wouldn't ask you to do that many steps. Even for homework, it'd just be tedious, busy work. Okay? At that point, you would want to go to Excel, which is accessible, or to a computer algebra system. Excel does this rather nicely. We'll talk about how to set it up in Excel, and we'll talk about how to notate the process. Okay? Now, I'm not doing a more complex approximation because you've already done them. You already know how to do it. So we're just kind of sticking with easy ones that I can more or less get right in my head. Okay? But as soon as you go to Excel or a computer algebra system, do anything. You do any kind of complicated mixture problem, population dynamics, stuff that we've been looking at, right? Logistic models. And so forth. See? I'm wanting to go to spring mass dash pot and RLC circuit models, but that involves higher order equations. So what I'm really wanting to say is just motion with drag. Okay? Or simple harmonic motion. I couldn't have that goes second order too, so we don't want to do that. Yeah. Okay? Make sense? Okay, so I'm going to, next we're going to write down just a formula for this method. Okay? Not that you want to actually use the formula, you want to be able to write it down because that helps you figure out how to notate the method so that you can get it into a computer algebra system or something of that nature.